floor to Dr. Xia. Thank you.
Okay, let's welcome Shan's presentation. The title is Continuous Purification of Wet Process, Phosphoric Acid by Hybrid Precipitation and Nanofiltration. Shan is from Laboratory of Membrane Material and Separation Technologies, Shanghai Advanced Research Institute, Chinese Academy of Science. So let's welcome Shan.
Thanks for the chairman. I'm very honored to have this presentation. My name is Shanshan Xu, a PhD student from Shanghai Advanced Research Institute. My supervisor is Professor Tao He. The topic of my report is Continuous Purification of Wet Process Phosphoric Acid by Hybrid Precipitation and Nanofiltration. My presentation includes 6 parts. Phosphorus is indispensable and mainly comes from phosphate rock, used to produce phosphoric acid, an essential chemical for the fertilizer and various chemical products, as shown in the figure. There are 2 midstream production processes of phosphoric acid, the wet process and the thermal process. The wet process manufactures around 90% phosphoric acid due to its low energy consumption and cost. However, the wet process phosphoric acid contains a variety of cationic impurities, thus is of low purity and low profit margin. So further purification is required to produce industrial-grade, food-grade, and electronic-grade high-purity phosphoric acids. The traditional purification method of phosphoric acid is solvent extraction technology, but it has shortcomings of large consumption of extractant loss, product contamination, high total cost, and complicated production line. It is still a challenge to purify wet process phosphoric acid with better and low-cost technologies. Phosphoric acid is known to be a weak acid. At low pH, phosphoric acid mainly exists as a neutral molecule, so we use nanofiltration membrane to remove multivalent ions and allow acid permeation based on the steric and charge factors. The nanofiltration process is simple and the energy consumption is low. According to the hydration radius of phosphoric acid and the impurities ions, nanofiltration membranes ideally fall into the MWCO of 120 to 213 Dalton. However, the wet process phosphoric acid contains a lot of impurities, which may cause member fouling or scaling, resulting in decreased member performance and increased energy consumption. At present, the long-term operation of nanofiltration in actual phosphoric acid system and member fouling or scaling is not clear. Thus, there are 2 key issues to be resolved. The first is member fouling or scaling mechanism in purification of crude phosphoric acid by nanofiltration technology. Another is designing a continuous hybrid process of wet process phosphoric acid purification. We first use microfiltration and ultrafiltration to pretreat the actual wet process crude phosphoric acid, and then use nanofiltration to remove impurities. We also use Hermia model to determine the fouling mechanism. In the microfiltration process, the EDS shows that the fouling or scaling elements include sulfur, fluorine, silicon, aluminum, and calcium. Aluminum salts mainly cause the colloid fouling. In the ultrafiltration process, we found membrane scaling caused continuously decreased flux, especially under the two bars. More serious scaling occurred. This is because ultrafiltration membrane scaling was mainly caused by external concentration polarization. The Hermite model calculation shows that the membrane scaling in ultrafiltration belongs to kick layer blocking. It is difficult to restore membrane performance by simple physical cleaning. The scaling elements in ultrafiltration membrane are sulfur, silicon, iron, and fluorine. No aluminum element, indicating that colloidal fouling caused by aluminum salts mainly occurs in a microfiltration process. Then we use commercial nanofiltration membranes, DL, DK, KH, to investigate the membrane fouling or scaling. The decreased flux and increased ion rejection showed that serious membrane scaling occurred on the nanofiltration membrane surface. In spite of this, the cation rejection can reach about 90%, and the phosphoric acid permeation can reach about 80%. The silicon and the sulfur rejection have a relatively low rejection rate and will lead to serious membrane scaling, so which should be removed in the pretreatment step. The scaling elements in the nanofiltration membrane are sulfur, silicon, iron, and fluorine. To sum up, scaling mainly occurs in total membrane separation process. The main elements are sulfur, fluorine, silicon, aluminum, calcium, and iron, which is difficult to be cleaned directly with DI water. It was not seen that magnesium did not participate in scalant formation in the total process. The particle size analysis showed that after nanofiltration, the solution is very pure. Stability and color were effectively removed. So nanofiltration can be well applied to purify phosphoric acid, but the problem of membrane scaling must be solved. On this basis, we designed hybrid precipitation, ultrafiltration, and nanofiltration process to purify phosphoric acid, as shown in the flowchart. Firstly, adding chemical reagents to remove scaling elements. Next, supernatant is diluted to reduce the osmotic pressure and adjusted pH below 2 to reduce the dissociation of phosphoric acid, and then filtrated by ultrafiltration. The nanofiltration permit of high purity is further concentrated to produce food-grade or electronic-grade high-purity phosphoric acid. The nanofiltration concentrate mainly includes magnesium, calcium, and phosphoric acid for producing calcium magnesium phosphorate fertilizer. Then we carried out many experiments about reagent types and ratios, and finally determined to add mixed reagents, named BCM. By adding a small amount of BCM reagents, the removal rate of scaling elements was about 90% or even 99%. The loss rate of phosphoric acid was below 5%. The patent is pending. except for calcium and magnesium ions, the concentration of other ions is very low, as shown in the table. Due to the high osmotic pressure, the pretreated solution was diluted 2 times for subsequent ultrafiltration and nanofiltration. As shown in the figure, the flux of the ultrafiltration membrane was very stable after pretreatment. After 3 cycles, the nanofiltration process was also stable and the ion removal rate was high. The average removal rate was more than 80%, reaching the target removal rate. However, the increased pH led to the decreased phosphoric acid permeation. So the solution pH was adjusted to 1. The formation of phosphoric acid doubled. Finally, we calculated the total cost of the hybrid process. Only 2,000 RMB per ton 85% phosphoric acid, far lower than the cost of solvent extraction and thermal process. To conclude, at low pH, phosphoric acid merely exists as a neutral molecule. Nanofiltration can remove multivalent ions and allow acid formation. Nanofiltration is a simple and low-energy technology. In the purification of crude phosphoric acid, serious scaling occurs on microfiltration, ultrafiltration, and nanofiltration membranes. The main elements are saffron, fluorine, silicon, aluminum, calcium, and iron. A new low-cost hybrid precipitation, ultrafiltration, and nanofiltration process was proposed to realize continuous purification of crude phosphoric acid. Now, the previous experiments were based on commercial nanofiltration membranes. The flux was low, and the phosphoric acid rejection was too high. There is a need to design high flux, low phosphoric acid rejection, and acid-resistant nanofiltration membranes. Now, we are preparing layer by layer acid-resistant nanofiltration membranes for the phosphoric acid purification. It is expected that phosphoric acid permeation will reach about 90%, and the acid flux can reach 20 lmh. Finally, we thank the support from NSF CAS, BRICS Foundation, and the help from 2 MST members. This is the end of my presentation. Thanks for your attention. Thanks for the chairman.
Yeah, very nice presentation, Shanshan. I have one question. Could you briefly introduce the market of phosphoric acid purification?
Thanks for your question. At present, there are about 10 million tons per year for phosphoric acid products. The processing capacity is about 5 times as much as the product. Now, the food grade and electronic grade high purity phosphoric acid on the market is mainly prepared by the thermal process, but the cost is high, about 5,000 RMB per ton 85% phosphoric acid. And another, the better process phosphoric acid is mainly produce the fertilizer, and the purification of wet process phosphoric is
is by solvent extraction, but the cost is 4,000 RMB per ton. So we design the hybrid process. We can reduce the cost to 2,000 RMB. That's all.
Yeah, thanks a lot. And in your recent work, you shows that your self-assembled NF membrane has a obvious advantage over commercial membrane. So what's your next step, and is there any development area for your work?
In the last plan, we will use our prepared layer membrane to purify the phosphoric acid. Because the layer membrane has a high flux, and the process can be precisely regulated. So we design the MWCO of the layer membrane about 200 Dalton. So it is expected the phosphoric acid permission can reach about 90%, which is better than the commercial nanofiltration membrane. That's all. Thank you.
Thank you, Shanshan. So have you done any temperature factor test? What about the application for phosphoric acid purification in the real case? What's the temperature requirement?
Yes, we test in the room temperature.
Okay. So it seems there's is there any other question from the participants? Okay, I think maybe our session has finished.